Okay, hello and welcome back everybody. We are on section 4.3 today, and we're finally going to be talking about PDEs as opposed to ODEs, right? So the main difference is that back last semester you were working with differential equations where the derivative was only occurring in a single dimension. And when it comes to PDEs, the derivatives inside of the equations are allowed to be taken in multiple dimensions, the same way that when we're working with scalar fields, we can take derivatives in either the x or the y direction, or z direction, and so on. So we've got two examples here in definitions, at least, and the first deals with scalar fields. And of course, a scalar field is just going to take a vector as an input, x, y, z, and perhaps it also depends on time. Okay, so it evolves over time and it has three spatial inputs. And then it outputs a single number, and a PDE of such a scalar field would just consider a single equation, because it would just relate the scalar values of the scalar field as the PDE. So let's look at this, and let's say maybe, for example, something like partial u partial x plus partial u partial y plus partial u partial z equals partial u partial t. It's a perfectly valid scalar valued partial differential equation. If we look at vector valued partial differential equations, vector fields, you'll recall, are basically just made up of three or more, however many dimensions the vector field is, but in many cases three scalar fields. And then if we were taking a partial differential equation that related the vector v to another vector, then we would actually have basically a system of three scalar equations, is the way we could perhaps interpret that. So just to give you a quick example, again, we'd have something like, if I just wrote partial v vector partial x equals 1, negative 1, 0, that should really be interpreted as partial v1 partial x is 1, partial v2 partial x is negative 1, and then partial v3 partial x is 0. Where the 1 is coming from there, the negative 1 is coming from there, and the 0 is coming from there. So we just want to make sure that we interpret maybe a vector partial differential equation as a system of partial differential equations. Okay, so moving on from there, we actually get into like the real examples that we care about in this chapter. And the first one we're going to talk about is the scalar heat equation. Why do I say scalar heat? Because heat is a single measurement, and we're never going to have more than one heat happening at a time. So this is a heat equation where we're measuring the temperature of three-dimensional space represented by the vector x, and u outputs the temperature. So the temperature evaluated at the point in space x at the specific time t evolves, that's what partial t would describe, according to this equation. And we can start to see our gradients show up here because we're taking partial derivatives. So in fact, it just evolves according to this equation. The F on the right-hand side is some sort of forcing term, or you can think about that as like inputting heat into the system. You have maybe a candle that's lit at some place. And of course, the heat output of the candle depends on time, and it also depends on where you're standing. So the change in the temperature of maybe every point in the room depends on the candle that's on the right-hand side as well as this, and this really describes diffusion. Maybe I'll mention that here. This is a diffusive term. We can think about this is like close to delta being our Laplacian. So we have a diffusive term there. This would be like a candle in the room, and then this would be like the change in temp over time. So that's what we want to think about when it comes to a heat equation, is that the change in the temperature over time is modeled by diffusion, and then maybe there's some forcing in the room. So we're going to talk about this a little bit more later, because we'll actually go about solving these later. But this is just a nice example, and we can also look at the nice example of the Laplace equation. Sometimes this is called a Poisson equation. So I'm going to comment on the difference. Laplace tends to refer to, if this is 0 on the right-hand side, we would refer to that as the Laplace equation. And if the right-hand side is non-zero, that's when we refer to it as a Poisson equation. But of course, they're very closely related. And in general, what this is describing is this kind of calculates the curvature of the scalar field, and it says I'm going to let the curvature of the scalar field be given by some scalar function. And when that scalar function is 0, we recover the Laplace equation. And then something that's kind of interesting is that this equation can actually be realized, as in you can solve it. You can solve this equation using the long-term behavior of the heat equation. So if I end up solving this equation and I take t, the limit as t goes to infinity, and then I would actually recover this equation, so long as, you know, t going to infinity of the function f actually converges right here. The wave equation is a very other common one. Oh, and in case anybody has forgotten how that's defined, this is defined as partial x squared plus partial y squared plus partial z squared. And that's going to show up down here as well in the wave equation. So in the Poisson equation, we have this Laplacian. That's why it's called the Laplace equation often. But the Poisson equation, we have a Laplacian inside of it, and that's equal to f. In the wave equation, we also recover the Laplacian. And these are really your second derivatives in space are basically balanced against the second derivatives of time. And that's all that's saying is that this kind of makes sense, because if this is measuring curvature, how does a wave change over time? Well, the wave changes directly in response to the curvature. So this is wave change over time. So actually, the more curved a wave is, the faster it travels. This is kind of a little fun fact for everybody to think about, is that the more curved a wave is, the faster it's going to travel. Okay, so that's just another example. These are kind of the three classic examples. That's why they're brought up here. These are the three examples that maybe if you take the right physics course, you'll be expected to solve by the end of the course, or maybe, of course, you know, this course as well. You'd be expected to solve everything by the end of the course. In these examples, they're all linear, so they're all pretty easy to solve. It's the nonlinear ones that get really tricky. All right, so Maxwell's equations is another great example, and you've probably heard about these. They describe the relationship between an electric field and a magnetic field. So every time you see B in physics, especially if it's a vector valued capital B, that's usually the magnetic field. Vector valued capital E is an electric field. Vector valued J is current, actually. So this describes the current in the system. So there's the Maxwell's equations describe the relationship between all of these. It's a system of 4 vector valued partial differential equations. Thankfully, once again, they're all linear, so they're not impossible to solve, but they're not exactly, I mean, even, you know, you're getting into a lot of dimensions here that this doesn't exactly get easy to solve. This is something that our computers can handle, and we'll learn how to handle these, I guess, in pieces in this class. And if you solve all of these together, then you perfectly describe a system of evolving electric and magnetic fields. Finally, we have this time-dependent Schrödinger equation. And I remember last semester you likely solved the time-independent Schrödinger equation. Perhaps you solved the time-dependent Schrödinger equation as well. But I can't quite remember. But in this case, we can basically increase, we can involve time, and we can increase our dimension up to 3. And then you'll recall our energy operator, which is really actually the Hamiltonian operator. So the Hamiltonian operator is considering potential energy V and kinetic energy h bar squared over 2m times the Laplacian. Okay, so this is your energy, and I realize I shouldn't call the Hamiltonian operator the energy operator, but the Schrödinger equation says that the one operator is exactly equal to the other. So E is the energy operator now given by this, and what this is really saying is that the evolution, let's look at this together, the evolution of a wave function psi, right, recall this is your wave function, is determined by the energy, which is given by h psi, in fact. So the energy of the system, which is h psi, describes how the wave function will evolve over time. And so if we put all those pieces in there, then that's what you end up with. Once again, this is linear, so it's not that hard to solve. Okay, there's one other thing I want to comment on before we move on to section 14.4, which is the heat equation. And I'm going to move over to the whiteboard for this. So what I want to talk about is, let's say, PDEs and initial or boundary conditions. So back in ODEs, we had this idea of either you would either have an initial condition And that would be like an example of that is that your differential equation, d dt of maybe position equals a function of time as well as position. And in fact, we would initialize somewhere at, let's say, 7. So this was called the initial condition. It's the place that the ODE is initialized at. It's saying when time is 0, where does my ODE start? And in fact, we don't have to restrict it to time being 0 because let time be 8 or 9 or -4 or whatever. But in general, an initial condition is saying I'm starting my behavior of my system from a single point. Whereas a boundary condition, I'll write this in red, a boundary condition was the situation where we would have you need at least a second order differential equation. So let's consider a higher order differential equation. Let's say d squared dx squared of y of x is equal to omega squared y of x. And in this situation, you'd have something like y at -pi is equal to 0 and y at pi is equal to 0. And what this is referring to in a boundary condition sense is that the behavior of my solution y has 2 points which are fixed in space. So I'll say 2 points fixed in space. And those are the boundaries. These are the boundaries. So that's something that you could have in ODE is you either have an initial condition where you're like initializing the ODE at a specific time, or you have a boundary condition where you have 2 points which have been fixed in space, and those are called the boundaries. In PDEs, it's not quite so simple. In PDEs, we often have both. Now the question is, why do we often have both? Well, the easiest answer is because PDEs evolve in both space, i.e. the boundaries, and time, which would be the initial condition. Right, so since we're evolving in space and time, these are kind of the 2 directions we're allowed to evolve in, but they're partial derivatives because of those directions. We are allowed to have the initial condition in time and the boundary conditions in space. And so what does a PDE often look like? I'll say this manifests like the following. So let's just take the wave equation, for example. Partial t squared of u is equal to omega squared partial x squared of u. So we're going to let this just be in one spatial dimension and one temporal dimension. Of course, most waves are 3-dimensional in space, but let's just restrict ourselves to 1 right now. And what this equation is going to have is both an initial condition. So we're going to have u, which you'll recall is a function of t and x. If I have a initial condition, then I'm evaluating this initially, as in the time step is 0, that's the initialization, and this is equal to some function. So this is what we would call a prescribed initial condition. And then similarly, the function has to have some boundaries in space. So instead of t being fixed at 0, now we have some boundaries in space. Maybe I'm back at -pi and pi, and those are now functions of time, and oftentimes those are restricted to 0 or something similar, where we just take a value in this spatial boundary. And in fact, since this was a partial squared, partial t squared, I need 2 initial conditions, so I'll add another initial condition on here. So we also have the first derivative in time. How should I notate that? Partial t of u at 0 and x, maybe that's g of x. And so we end up with 2 initial conditions because we have 2 temporal derivatives. So you have 2 initial conditions, and then you have 2 boundary conditions, and these are your boundaries because we have 2 spatial derivatives. So that's just something to keep in mind. We in PDEs, we often have both. We're allowed to have both initial and boundary conditions at the same time. And then there's a little glossary I'll call this the glossary of what we call boundary conditions. I'm only going to look at 2 of these, not 3. I'll go to 3. Glossary of boundary conditions. Glossary is, and I'm going to define a few things for all of you. We have something called the Dirichlet. This is a nice, fun French word that you get to pronounce. I used to think it was Dirichlet. It is not Dirichlet, it's a Dirichlet. That's something to get used to. So a Dirichlet boundary condition. Boundary condition is, these are your classic zero derivatives in space, and they are just equal to a function of time. Okay, so what's an example of that? The one we just saw, u at t negative pi, u at t and pi, these are both equal to 0. And it doesn't look like that's a function of time, but of course 0 is technically a valid function. If I wanted to say f of t equals 0, that's valid. So that's the Dirichlet boundary condition. The Neumann boundary condition, I'm just going to erase it and now replace the word with Neumann. The Neumann boundary condition is no longer classic, so I'll get rid of the word classic. It's a first derivative. One derivatives in space. So in higher dimensions, this would be like nabla, right? So we have some sort of, and in fact, it's usually nabla, I'll reverse that. It's usually normal dot nabla. So we have some normal vector in space. This is the normal directional derivative. And what's a nice example of this? I'm going to get rid of these as the example. A very common example would be something like, let the boundary of omega exist. That's why it's a boundary condition. Exist. And n be the normal vector to the boundary. And of course, if that's the boundary of a surface, or a boundary of a three-dimensional object, then it's actually a surface. And this is why we care about calculating surface normals. A Neumann condition, an example would be n vector dot the gradient on u evaluated in time at the boundary, on the boundary, in space, is equal to 0. That's a very common boundary condition. So that's just saying that the normal derivative of my solution needs to be equal to 0. Sometimes rather than writing the evaluation on the boundary like this with d omega, we'll write x and then we'll say evaluated on omega. Either one's the same. So that's a Neumann boundary condition where we have first derivatives in space. And then finally, the last boundary condition that's actually a bit easier to talk about is the periodic boundary condition. And this would be where any number of derivatives, but often 0, and we have the relationship that u of t at one end of the boundary at minus pi is equal to u of t at the other end of the boundary, maybe it's pi. So the fact that they're equal to each other, I'll say values are equal at the boundary. So that's just a glossary of these terms, because you recover different solutions to a PDE with different boundary conditions. And so these are all useful for their own reasons. Anyway, that's all I have. I'll see you in class. Bye.